This is the transformer circuit. Let me increase the audio level here. Is that better? Better? Alright. Sorry if the source voltage audio might have been down a little bit. Okay. This is the transformer quote-unquote circuit. Now, this is... I'm scratching my head literally right now. I'm scratching my head a little bit on this one because you don't have to have a complete circuit. And what do I mean by that? It means you don't have to have the return from the source, the signal generator, be attached to the circuit in order for this to work. Now, I can't explain that to you right now, but I'm gonna find out because I don't understand it either. However, the concept is there of what we're trying to do for your experiment. Now, this is an audio transformer right here. I got my pointer. Invader! Okay, here's the transformer. Okay, it's an audio transformer, meaning that it works in the audio range, which is 20 hertz to 20 kilohertz, but I think this one's rated for up to 100,000, maybe 150k hertz. Okay, meaning that your input signal, in order for this to induce the current, you have to have a frequency between 20 hertz and 150k hertz. Anything outside of that range and the output goes to zero. All transformers are rated this way. Most all electronic components are rated with a bandwidth, what's called, from the range of frequencies in which they work, except for resistors, which are very passive. So what you see here is this is the signal generator input. It's still at 5 volts peak to peak, 1 kilohertz. This is the probe for the oscilloscope. Okay, this is the probe for the voltage on the voltmeter. Okay, so the signal comes in, goes through the resistor, black wire into the transformer. Now you notice here that the other end of the input circuit is out. Okay, this is what my conundrum is here. I don't really understand. So let's go over here. The top signal is the input voltage. The bottom signal is the output voltage of the transformer. Now, this is 5 volts peak to peak, source voltage. This is only 2 volts peak to peak. Okay? So I set my ground, okay, right about here. Where's my level? Okay, 2 volts peak to peak. So we got 5 volts on the input, 1 kilohertz, but I only have say 1.3, okay, at 2 volts per division. So that's, say, 2.2 volts peak to peak. So it went from 5 volts peak to peak down to 2.2 volts peak to peak. So there's a loss occurring somewhere. Okay, now, unfortunately, I couldn't find the spec sheet on this audio transformer. I don't know what the turns ratio is. I would suspect, though, that an audio transformer, which is just to isolate, is going to be the same number of turns on the primary as the secondary. Okay, but without knowing that for sure, I don't know. I can't explain what the loss in voltage is. Now, back to the circuit, you'll see that I have the gray probe. The gray probe is attached to the output of the transformer, the brown wire here. Okay, it's tough to see, but this one's brown. Okay, and it goes through these two resistors. It's about 8 ohms, it's 8.3 ohms or something like that. That's the impedance of a speaker. This is an audio transformer. Okay, so the load is going to be a speaker, which is usually about 8 ohms. So that's why there's two resistors here. However, it doesn't really seem to matter, because although the red wire is attached to the circuit, right? The secondary circuit goes through the brown wire, through the resistors, through the red wire, and back to the transformer. Okay, that completes the circuit. Okay, we completed the circuit. Okay, the bottom waveform is the output of the transformer. But trust me, I'm going to go over here and I'm going to disconnect the red wire from the circuit. Okay? I just pulled off the red wire from the secondary. Okay? And it makes no difference. Now, why that is, I don't know. Now, back to the primary circuit. I noticed the same thing on the primary. It doesn't matter what value of resistance I have after the function generator, through the resistor and into the transformer. I put in a 10K and a 100K resistor yesterday, see if it made any difference. Made no difference at all. So what I'm going to do is I'm going to show you is I'm going to disconnect from the resistor. Okay, so you see the output goes to 0 because now I have no source, and I'm going to bypass the resistor and I'm going to go straight into the transformer with the signal generator. So it makes no difference. And again, the primary circuit it's not a complete circuit. Okay? Because here's the output of the primary on the transformer. It's not connected. Also, there's the negative of the function generator. It's simply connected to the voltmeter to measure the RMS voltage. That has to be grounded in order for that to work. Okay, maybe I should have told you that on the other video, that you have to have a ground when you touch your hot to test the measure the voltage. The other side has to be grounded. Okay, that's still measuring 3.53 because it's attached to the, even though it's on the other side of the resistor. Okay, the voltage, it's an open-ended circuit on the other side. It's an open, it doesn't go to ground. Okay, so since there's no current in here, right, then the voltage simply there's no voltage drop because there's no current. So that's why I'm still seeing, I can measure on either side of the resistor and I'm still going to get the VRMS of 3.54. So what's next? Well, if I connect, I disconnected the voltmeter. If I connect the output of the transformer to the function generator, right, to complete the circuit there, well, look at that. That's not what yeah, this thing is funky. It's inverted. Very interesting. I didn't see this before. And it's actually at 1 volt per division, 10 volts per division, my output here is almost 20 volts peak to peak. So it went from 5 volts peak to peak on the input to 20 volts peak to peak on the output, and it's inverted. Ground them. Let's put them both in the middle. Turn them back on. Okay. Here's your source voltage, channel 1. Alright. So the source voltage is at 1 volt peak to peak. 1, 2, 3, 4. So it's actually gone down. If I take the function generator probe off, it goes up. So I'm losing a little bit of source voltage. Okay. But my output looks pretty good. And it's increased. So maybe the turns ratio is 2 to 1. Or in this case, it goes from 4 or 5 volts on the source to 10, 20, 30, 38 volts. So call it 40. So that's a 1 to 4 turns ratio on the auto transformer. I have to find out, I got to do the specs on that. But anyway, that's your, let me change the frequency. I'm going to hit the button. I'm going to go to 10K. Change my time base. Okay. Still have a pretty good, alright, but now you see how the output has gone down. My input actually gone up. So depending on the frequency, circuits have different behaviors depending on your source frequency. Alright, if I go to 100K, let's see what that looks like. Okay, here's my source voltage. That's back around 5 volts peak to peak. Alright, and now I'm down, I think I'm down a little bit more, right, on the output voltage. Okay, so now it's at 3 divisions. That's 30 volts. I go back to 10K. Well, now it's down to 2.5, 25 volts. 100K. 30 volts, and if I push it to a megavolt, alright, now you got nothing. So you've completely, it can't handle those high frequencies. So let's go back to 100K. And if I crank up the frequency, let's see if I can see it go down. See it start to drop? Right? Because I can't go any higher. That's 225 kilohertz. But the point is that you see the voltage changes with frequency. Now I'm way down. Okay, what is that? 202K hertz. This is the low end. There's a 200 hertz. So you see how the bandwidth, the output changes with frequency. Alright, this is getting a little long. I'm going to shut this off.